My name is Nick Braithwaite. I'm currently the Executive Dean of the STEM faculty, and I'm here to welcome you all this evening. But before I go any further, I have to tell you that we haven't planned any fire alarms, so if it does go off, we should leave quickly in an orderly fashion, either through there or through there, and assemble where everybody else is assembling. Well, it's no good to be telling you where it is because it's disorienting going out if you'd be pointing in the wrong directions. Okay, now we have some people joining us online. We're live streaming this, so welcome to those people in particular. And let me say also that because of that, if we're asking questions afterwards, we've got some roving mics, and if we can let the mics get to the people before they ask the questions, then those online will be able to hear it. We'll do what we can to keep those online engaged as if they were in the room. We're also going to be using Padlet to allow people to engage during these lectures and to provide feedback at the end if necessary. There is a QR code that I'm told works extremely well from the front row. If you're further back, then there's bit.ly/OpenStem, and that should connect you there as well. Okay, now, what have we got? We've got a series of lectures, and this is the first one. They're called OpenStem Talks. This is the first one on this, a very special and auspicious day for the Open University, because it is now 50 years since our charter was delivered to us. So the first 50 have gone down okay. Our mission now is to get the next 50 started. And that's what we're doing with this series of talks. We're going to cover a whole range of STEM in these talks. Some will be lectures, some, as we got tonight, 2 lectures. Some might be a debate, and some may include some demonstrations. I certainly hope those will be occurring. And OU STEM YouTube channel will be the place to watch them. We also have Facebook presence as well. Now tonight, let's get down to tonight. We've got 2 speakers. The first one is Professor Andrew Holland, who's going to talk about the Clockwork universe. Wrong Andrew, Nick. Andrew Holland. Did I say Andrew Holland? Right, can we just cut and start again? That's terrible. Will you forgive me? He won't even forgive me. We do this a lot. And now, tonight, we have 2 incredible lecturers, far better than what you might have heard just now. We have Professor Andrew Norton. I think I'm reading this too. Who's going to talk us about something which Andrew Holland knows nothing about. Andrew knows about the Clockwork universe, adventures in time domain astrophysics, and that's what I know. I've known of Andrew all the time that I've known these last 20 years or so. That's his speciality. He started, as the other speaker did, at the University of Leicester. They got their PhDs from there at any rate. And I've just discovered that the second speaker taught the first speaker how to use a telescope back in those days, and then sometime later the first speaker taught the second speaker how to use a telescope when they were here. So they've been exchanging views on things astronomical for some time. Anyway, where is Andrew now? Well, after he postdoced at Southampton, he came here. He's now risen to the dizzy heights of Professor of Astrophysics Education, and he's led the presentation of quite a lot of modules in physics and astronomy, space, science modules he's been involved with too. In the undergraduate and the postgraduate curriculum. His research focuses on the time domain astrophysics that he's going to tell us about, and compact interacting binaries and wide field photometric surveys. Now, Andrew has also been a vice president of the Royal Astronomical Society, and he's extremely well connected. There is something called an Erdos-Bacon Sabbath number, which shows your connectivity to mathematicians, actors, and heavy metal rock bands, and you have to have a low score on that to be anybody. Andrew's is 13, which is apparently quite a low score. Well done. Now, he's also written various things like 60 Seconds Adventures in Astronomy. I hope you're going to talk for more than 60 seconds tonight. And what else has he done here? Oh, he's interested in Doctor Who and Star Trek. Well, these people are. Let me go on to the second lecturer. Professor Simon Green. Did I get that right, Simon? Yeah, okay, he's the only Simon I know. Near-Earth asteroids, a matter of life and death. That's his topic tonight. Well, he's a professor of planetary and space science in the Open University's School of Physical Sciences, same home as Andrew. I've told you where he got his PhD. He's interested in these small objects out there in the solar system. He's been on missions that have gone to comets. He's worked on missions that have collected stardust, and he's got unpronounceable comets that were visited here in the Rosetta mission. but he's also been to Titan and Saturn with his missions. So he's been around the solar system a bit. So we've got the stuff out there, and we've got the stuff more local. What a night it's going to be. Let's see. I should tell you also this key fact about Simon. Asteroid 9831 is named Simon Green. No space. Simon Green, in recognition of the work that he's done on asteroids and trans-Neptunian objects. Right, I'm going to hand over to Andrew in just a moment. I'd like to thank you for joining us right now. There will be some questions afterwards. If you're here, we can offer you some refreshments afterwards downstairs. If you're online, we'll tell you what they're like. Okay. And I think that's probably enough for me. So let's get Andrew to come and deliver the first talk.
Thank you very much, Nick. Thanks for the introduction, and thanks everyone for coming. It's nice to see so many familiar faces here. So the subtitle of my talk is Adventures in Time Domain Astrophysics. I'm going to take the chance in the next half an hour to tell you about some of my favourite astrophysical objects that I've investigated over the years and a couple of the time domain astrophysics projects that I've been involved with. So this is my opening question, which is on the Padlet website that Nick mentioned. Does the universe run like a machine? And it's a question for you to consider, if you like, and some little subsidiary questions there on the left about how stars might vary, how they might move, and how we might measure that, which might trigger some things for you to think about, and which hopefully I'll give you answers to as we go along. And some of you may recognise the clock there, which is also at Leicester University. So the foundation of really what I'm going to talk about really goes back to Isaac Newton. 350 years ago, he developed his theory of gravity, and that describes how planets and stars move through space and how things vary in this clockwork manner that I'm going to talk about. He was also one of the first people to use a telescope to observe the night sky, and one of the first people to recognize that you could split white light into its constituent colours into a spectrum using a prism, and all of those aspects will have relevance to what I'm going to be talking about shortly. It's important to really think about, when we talk about a clockwork universe, measuring time, our measurements of time really are rooted in space, in astronomy. After all, as you know, the Earth spins on its axis once every day, the Moon orbits the Earth once every lunar month, and the Earth and Moon together orbit the Sun once every year. And these are then three clocks that are present in our solar system that form the basis of our measurement of time to a large extent. And when we think about stars out there in the galaxy, some of which you can see in the background here of this picture, they too have their own inbuilt clocks. They vary and they move in certain ways, and that's what I'm going to be telling you about. One of the important things to realise about stars, though, again, you can see from this background picture, even to the best telescopes, they generally appear as just a point of light. Now, that's fine, because we can see that these points of light have different brightnesses, and indeed they may vary in brightness with time, and that's the basis of what I'll talk about in the first part of my talk on light curves of stars, how the brightness of stars vary with time. The other thing we notice in a picture like this is that stars have different colours, and that tells us that they emit different spectra. They emit different proportions of light at different wavelengths in their spectrum. And measuring the spectra of stars can actually tell us about how they move through space. And I'll come to that in the fourth and final part of my talk here. In between those two parts, I will tell you about two of the projects that I've been involved with over the years, SuperWASP and Zooniverse, and I'll explain what those are. And I'll give you just a couple of examples of the many variable stars that are amongst my favourites, things that I've studied both in visible light and in X-ray light, and I'll show you those. So let's start then with thinking about light curves and what a light curve is. The simplest measurement we can make in astronomy really is just taking an image of the night sky, and there's one there shown on the left, lots of stars in that. And what we can do, if we choose, is take a particular star in that image and measure its brightness. We can then take repeated images of that same field, each of which contains that same star, and we can measure the brightness of that star in each of those images, and we can string all those measurements together to make a light curve, and that's what I show on the right there. Each little black dot is a measurement of brightness of that one particular star at a particular time, and at the top there we have a light curve spanning about 8 years, and below that a zoom in to about a month's worth, and below that just a zoom in on a few nights of data. And in that zoom in, I think you can see already that that star is varying in brightness in a fairly characteristic and periodic way. If we want to understand how a star is varying in brightness, we want to see what periods of variation are present in that light curve, and how we do that is shown here. So on the left in red is a light curve. That red trace shows how the brightness of a particular star is varying with time, and we can split that up, deconstruct it if you like, into 3 separate signals shown by those purple traces. They each have a different period of variation, a different frequency. They each have a different amplitude. And if we add those 3 purple traces together, we get back to the red light curve that we started with. But one way of displaying that information in those 3 purple traces is as shown on the right in what we call a power spectrum. This is a plot of amplitude against frequency. So each one of those 3 signals that form the red light curve has its own characteristic frequency, so we get 3 spikes in this power spectrum. And if we look at the data in that representation, we can say, yes, that light curve contains variations at those 3 particular frequencies, those 3 particular periods of variation. And the mathematical process of going between the 2 we call a Fourier transform. The details of that are not important for now, but the point to take away is that we can analyze any light curve, such as the one in red shown there on the left, into its different components, as shown there on the right. So if I go back to that light curve I showed you just a couple of slides ago, and we take the power spectrum of that, we see that it actually contains 2 distinct signals, a low frequency signal corresponding to a period of 5.1 days, and a higher frequency signal corresponding to a period of 1.8 hours. So whatever this particular star is, this point of light, it contains these 2 clocks, these 2 periods of variation. What we can do is fold that light curve at each of those periods in turn. By folding the light curve, I mean, if you imagine that light curve stretched out on a strip of paper, and you just take a 5.1 hour segment of it, fold that onto the next 5.1 hours, and the next, and so on. So we overlay all those repeated signatures at 5.1 hours. We get something as shown on the left there, and the red line shows the average of all those many, many cycles added together. And that's a very characteristic light curve shape that we recognize as coming from something called an eclipsing binary star, shown in the cartoon at the bottom. In an eclipsing binary, we have a pair of stars orbiting around their common center of mass, and once per orbit, star number 1 passes in front of star number 2, and star number 2 passes in front of star number 1. So we get an eclipse each time, and that's the characteristic shape we see there. Now, if we take that same light curve and fold it now at the shorter period of 1.8 hours, we see this rather different shape, this sawtooth or triangular shape. And this is characteristic of what we recognize as a pulsating star. It's literally a star that's getting bigger and smaller, brighter and fainter, cooler and hotter as it does so every 1.8 hours. And so what that's telling us is this point of light that we've observed the light curve for contains 2 stars as an eclipsing binary, but one of those 2 stars is also a pulsating star. So these 2 clocks, these 2 regular periods of variation are both present in this same star. Now, that light curve and some others which I'll show you shortly were obtained with this project called SuperWASP, the wide-angle search for planets. SuperWASP consists of 2 installations, one in La Palma in the Canary Islands, one in South Africa, so that we can see northern and southern hemisphere skies simultaneously. As you can see, it contains 8 of these lenses on a single robotic mount, each of them only about 14 centimeters across, so they're quite small telescopes, but they're very wide angle. So they take images such as the one shown there in the bottom. It's about 15 times the diameter of the full moon. So a typical image might contain 100,000 stars in the one image. And what we did with SuperWASP over the course of a decade or more was just take repeated images of the night sky, minute after minute, hour after hour, night after night, year after year, and we built up billions of data points from this. In fact, we have light curves of 31 million bright stars, and they're all over the sky, apart from the galactic plane, the plane of our Milky Way, where the stars are just too close together to separate with these small telescopes. And the important point about these light curves with SuperWASP is that they have a long baseline over a decade of measurements, as I mentioned, but they also have a high cadence. That means we have multiple observations of each star every night, many per hour in some cases. So the main aim of SuperWASP was to detect transiting exoplanets, planets orbiting other stars that pass in front of the star as seen from our line of sight. And it's been very successful at that. When a planet the size of Jupiter passes in front of a star the size of the Sun, it will block about 1% of the starlight, so causing this characteristic dip in the light curve. And from that you can work out the size of the planet, and from other methods that I'll talk about later, we can also work out the mass of the planet. So SuperWASP has found about 160 of these transiting exoplanets. They're all what we would call hot Jupiters. They're about the size and mass of Jupiter in very close orbits around their star, so they're very hot planets. And the graph on the right there shows those 160 planets with orbital period up the left, ranging from about 1 day to 7 days, and the mass of the planet from half a Jupiter mass to a few Jupiter masses along the horizontal axis. But that's only 160 exoplanets, and I said there were 31 million light curves there. So what I spent a lot of time doing over the last few years was looking through all 31 million of those light curves to see if I could find signals of other variable stars. Now, I wrote programs to do this and ran them on our computing cluster here at the OU. It took 100 years of computing time, but luckily I was able to run this on 50 computers simultaneously, so it only took 2 years of real time. And in those 31 million light curves, I found 1.6 million periodic variations, with periods ranging from about 1 hour to 1 year, shown in that cumulative histogram there on the right. So 1.6 million possible periodic variable stars in this whole data set. And here's just 6 of those 1.6 million folded light curves, and you can see a variety of profiles, a variety of shapes. These correspond to things like pulsating stars, eclipsing binary stars, rotating stars, some of unknown type and some that may just be junk. Each of those light curves that I've done there is plotted over 2 cycles, repeated, just to help you see the variation that's going on. What I've done with those 1.6 million light curves is upload them to this website called Zooniverse. Zooniverse is a citizen science website where volunteers can take part in real science experiments. There's a lot of astronomy experiments on there, but they cover other areas of science too. And in my project that I've created there, SuperWASP Variable Stars, the task for volunteers is just to try and classify these light curves into the various types, pulsating stars, eclipsing binary stars of different types, and so on. So if you'd like to join in, please do go to zooniverse.org, search for SuperWASP Variable Stars. You can follow the little tutorial there and start classifying stars for yourself, and who knows what you might find. So the light curve I showed you to begin with, that was from SuperWASP. This light curve I'm showing you now is probably the favourite amongst all those many millions of light curves with SuperWASP, my favourite object that we've discovered so far. Now, we may find something better yet to come, but this is my favourite so far. It's an unremarkable star, goes by that name, Tycho 3807759. It's just a single point of light in the SuperWASP images. There's its light curve in the middle, 2 years worth of it anyway. When we analyse that light curve to look at what frequencies or periods are present in it, we see 2 sets of signals in the power spectrum. One corresponding to a period of 5.5 hours, and another set, which are all multiples of each other, integer multiples of each other, corresponding to a period of 1.3 days. So there are clearly 2 clocks in this system, a short period one, 5.5 hours, and a longer period one, 1.3 days. When we fold that light curve at those 2 periods in turn, this is what we see. The one on the left is the 5.5 hour period, and this is a very characteristic shape that we recognise as being a contact eclipsing binary star. The 2 stars in this system are so close together, they're distorted into this sort of pear shapes, and as they orbit around each other every 5.5 hours, we get this continuous variation in brightness, up and down, twice per orbit as one star passes in front of the other. It's a very compact system. You can see the size there for the diameter of the Sun by comparison. So it's a very, very compact system. If we fold the same light curve on the longer period, the 1.3 day period, we get this other eclipsing binary light curve, now with very narrow, sharp eclipses, well separated. So this is a detached eclipsing binary star. The two stars are well separated, they're not so distorted, and they just repeatedly pass in front of each other twice per orbit. So what we know so far then is this particular star contains at least 4 stars in 2 eclipsing binaries. As it turned out, this particular object has had another surprise in store for us, which I'll come back to a little bit later in my talk. Now, so far I've just talked about optical, visible light. We can study some stars using other electromagnetic radiation they emit, for instance, X-rays. And I spent a lot of my time, not least when I was at Leicester University, working in the field of X-ray astronomy, including using some data from this particular satellite, ROSAT, the joint German-British Röntgen satellite X-ray observatory. And this is now an X-ray light curve of a particular star called TX Columbi. So what we're plotting here in this graph is just the brightness in X-rays of that particular star over the course of about 1 day or so. If we analyse that light curve, we see quite a complex pattern of periods or frequencies in there, but the 2 dominant signals are at 5.7 hours and 32 minutes. Now what this object is what we call a magnetic cataclysmic variable star, and this very nice little animation shows what we think might be going on. We have 2 stars very close to each other, a red dwarf star, something much cooler, fainter and smaller than the Sun, which is distorted into this pear shape by a very dense object called a white dwarf, shown in blue there. The white dwarf is the remnant of a star that was initially maybe a few times the mass of the Sun, but has shed its outer layers and collapsed down to be something about the mass of the Sun or less, but the size of the Earth. So it's very dense, has a very strong gravitational field, so strong it's able to pull material off its companion. And we call this an accretion process, as that material gets channeled from the red dwarf down to the white dwarf. The material starts to spiral round the white dwarf and forms this structure we call an accretion disk, but because of the strong magnetic field, it truncates the inner edge of that accretion disk, material attaches to the magnetic field lines, and then channels down to the north and south poles of the white dwarf. And as it hits the white dwarf, it speeds up, gets very fast, gets very hot, and that's where the X-rays are emitted. So as you might have guessed, the 32-minute period that we see is actually the time it takes the white dwarf to spin on its axis. It spins every 32 minutes, presenting a different aspect of this accretion flow to us, and so we see that variation in the X-rays every 32 minutes. The 5.7 hour period is simply the time it takes the 2 stars to orbit around each other. So that's a cartoon of how we think it may look. Here are the results of some other work that I did a few years ago, where we build a simulation of the system inside the computer. So inside the computer we build a computer program that contains knowledge about the equations that control the gravity, the equations that control the magnetic forces in the system. We release packets of gas from the end of the red dwarf star there and see how they flow under the influence of those forces and see how they end up on the white dwarf. And the 4 animations shown here then, they're all for the same orbital period, the same period that the 2 stars orbit around each other, but in each one the spin period of the white dwarf is different and the magnetic field strength of the white dwarf is also different. And you can see we get different types of accretion flow, ranging from quite puffed up accretion disks to very diffuse disks to a more stream-like flow, or something that's rather ring-like with material channeling onto the field lines from there. So with these sorts of simulations we can try and understand how these things evolve with time, how they behave, and what the physical properties of the systems are. The final thing I want to talk about, having talked about just brightness measurements so far, is to think about spectra of stars. Now, going back to visible light to begin with, we know that with a prism we can split white light up into its component colours, colours of the rainbow. If we look at the spectrum of a star, we might see something like the image at the top there. We see the band of colours, but superimposed on it are these dark bands in the spectrum. They're what we call absorption lines, and they're due to absorption of particular wavelengths of light by certain elements, certain atoms in the outer, cooler layers of a star's atmosphere. If we convert that coloured representation of the spectrum into a graph, we might get something as shown on the left. This is 3 segments of the spectrum ranging from the violet part of the spectrum at a wavelength of about 4,000 angstroms through the blue into the green at a wavelength of about 5,000 angstroms. And in that graph then each dip in the graph is an absorption line corresponding to a particular element, a particular atom in the outer part of the star's atmosphere. And I'll come back to the spectrum of this particular star in a moment when I've shown you how these are useful. The reason spectra are useful for us, one of the reasons they're useful for us, is because of the Doppler effect. Now, the Doppler effect will be familiar to most of you, I'm sure, in the context of sound. We know that as a vehicle is coming towards us, the sound waves get bunched up in front, and so our ears perceive a higher frequency of noise coming from the vehicle as it approaches. As the vehicle recedes, so the sound waves get stretched out behind it, and our ears perceive that as a lower frequency of sound. Well, we get just the same thing with light. So in the system shown there, the yellow and blue, imagine that's 2 stars orbiting around their common centre of mass, seen from above, and then at the bottom seen from the side. So at some points in the orbit, that yellow star, say, is moving towards us, and at some points it's moving away. When it's moving towards us, the light waves it emits get squashed up, and so any features in the spectrum get shifted towards shorter wavelength, towards the blue part of the spectrum. As that star moves away from us, so the light waves get stretched out, and any features in the spectrum get shifted to longer wavelengths towards the red part of the spectrum. So as shown in the bottom bit of the animation there, you can see those spectral lines alternately moving to the blue and the red. This is the one equation I'm going to show you in the talk, the Doppler shift equation, which just tells us that the shift in wavelength, delta lambda, divided by the original wavelength lambda, is equal to the speed at which the star is moving, divided by c, the speed of light. Now we know the speed of light, we know the original wavelength of the lines, we can measure the shift in the wavelength, so we can work out the speed at which that star is moving. And we can then plot a graph of speed against time, which is shown in the top right part of the animation. And we call this a radial velocity curve. So it's a curve of the radial velocity, the velocity of the star away from and towards us as a function of time. So just from measuring the spectrum, we can then tell how fast that star is moving towards or away from us. So if I go back to that double eclipsing binary star I mentioned a while ago, we went and took spectra of that. Now with a bigger telescope, we could see clearly that this was not 1 point source, but 2 point sources. That's fine, we thought. That's the 2 eclipsing binaries we were expecting to see. And when we looked at the detailed spectrum of one of them, the 5.5 hour binary, we saw 2 sets of spectral lines moving backwards and forwards every 5.5 hours. So we're able to plot that upper radial velocity curve for those 2 stars. When we looked at the spectrum of the other pair of stars, as we thought, there were 3 sets of spectral lines there, 2 of which moved back and forwards every 1.3 days, but the 3rd set of spectral lines, shown in green on that bottom graph, stayed pretty much constant. So here we've got a triple star. 2 of them are orbiting around each other every 1.3 days, and presumably that eclipsing binary and the 3rd star are orbiting around each other with a much slower period, perhaps a few years, too long for us to measure in this short duration of observations. So this object, which initially to SuperWASP appeared as a single point of light, is actually 5 stars. It's a doubly eclipsing hierarchical quintuple star system containing a close eclipsing binary and a triple star, where the triple star itself includes another detached eclipsing binary. And from the radial velocity curves that we measured and the variations in brightness as well, we're able to work out things like the masses and the sizes of each individual star, how far apart they are, how long they take to go around each other, and so on. And as I say, that's probably my favourite of all the objects that we've found so far amongst the SuperWASP 31 million. The final object I want to tell you about goes back to X-ray astronomy, and this is another class of objects that I worked on for a number of years, so-called accreting X-ray pulsars. This particular object is called Vela X1. It consists of a neutron star, accreting from the wind of a supergiant star. Now, what are they? A neutron star is the collapsed core of a very massive star. Something that was initially maybe 20 times or more the mass of the Sun has undergone a supernova explosion, shed most of its material, and the core of that star has collapsed down to become this rapidly rotating neutron star. It's maybe the mass of the Sun, or even twice that, but it has a size of only 10 kilometers across, so it's immensely condensed, very, very dense indeed. And it's orbiting this supergiant star, something much more massive, much more luminous, much hotter than the Sun. And the two go round each other every 9 days or so. The supergiant star has a strong stellar wind, emitting lots of material into space, which the neutron star is able to sweep up as it orbits. And by a mechanism that's still not completely understood, having swept up that material, the neutron star then emits these beams of high-energy radiation from its poles, shown as this sort of lighthouse beam effect. So as it spins on its axis, so this beam of X-rays sweeps across our line of sight twice for every spin of the neutron star. So as shown on the left there, this is now a plot of the X-ray emission over the course of the spin of the neutron star, and every 283 seconds we get a double burst of X-rays as first one beam and then the other beam sweeps across our line of sight. So we can understand this system again using the Doppler effect or versions of it. If you look at those bursts of X-rays coming from the neutron star, as the neutron star is coming towards us in its 9-day orbit, so those bursts of X-rays appear to arrive at a slightly quicker rate. And as the neutron star moves away from us, so those bursts of X-rays appear to arrive at a slightly slower rate. We can measure a sort of time delay, a time advance and a time delay as the neutron star goes around its orbit. And that's what's shown in the left-hand panel there. And from that variation, we can work out the speed at which the neutron star is moving in its orbit. It turns out to be about 280 kilometers per second. Now, they weren't my measurements, but what we did is shown on the right. We took visible light, optical spectra of the supergiant star. We measured it over the course of 3 weeks, actually, 21 nights, and we measured the spectrum night after night, again and again, and we measured the Doppler shift of the spectral lines from that supergiant star. And when we plotted those on this 9-day period, this is what we found. It showed us that the supergiant star was moving in its orbit at about 23 kilometers per second. Now, combining those two speeds, the speed of the neutron star with the speed of the supergiant star, plus a few other bits of information we had about the orientation of the orbit and things like that, we were able to weigh the two stars in that system and able to figure out that the neutron star has a mass of 2.3 times the mass of the Sun, and the supergiant star actually has a mass of 28 times the mass of the Sun. So, using spectroscopy, we were able to weigh the two stars in that system. So everything I've talked about then has been about variability in the sky, variability of stars. And this field of astronomy, I think, has a bright future. I'll just show you one example now of something that's coming online in a few years' time. This is called the Large Synoptic Survey Telescope. It's being built in Chile on a mountaintop there, and it will become operational in just a few years' time. It will observe all the sky all the time. It's quite a big boast, but that's essentially what it will do. Like SuperWASP did, really, but remember SuperWASP had lenses that were just 14 centimeters across. This telescope has a mirror that's 8 meters across. So not only will it do very wide field astronomy, doing images of very large patches of the sky, it will also be able to see very faint objects, much, much fainter, millions of times fainter than was able to be seen by SuperWASP, for instance. And it will just repeatedly image the night sky again and again, night after night, for many years. The plan is that it will image the entire sky twice a week, each through 6 or 7 different filters, different parts of the visible spectrum. It will discover many, many periodically variable stars, I'm sure. It will also discover many transient objects, things that flare up and disappear night after night. So watch this space, as they say, for news of the LSST. So my almost final slide then is to return to the question I asked you at the start: does the universe run like a machine? I suspect well, I hope I've convinced you that to some aspect, indeed, it generally does. I've shown you that various stars, white dwarfs, neutron stars, regular stars, all spin on their axes with periods some as short as a few seconds, some much slower, up to months or more. Pairs of stars orbit each other, again, some with periods as short as a few minutes up to much longer periods, as long as you like, really. And actually, stars can exist in hierarchical multiple systems, combining binaries and triples up to any number of stars, really. All stars really have a variable brightness as well. At some level, all stars are variable. It just depends whether we can measure that level of brightness variability with the size of telescope that we have. And I've shown you that the movement of stars can also be revealed, not least by the Doppler shifts in their spectra. So that's a few of the highlights of things I've worked on over the past few decades. I hope you've enjoyed hearing about them. I'd just like to put up that slide to acknowledge assistance and help I've had from many people over the years, not just here at the OU, but former postdocs who've worked with me and postgraduate students and collaborators elsewhere, one or two of whom are in the audience, I know. So thank you very much. And that's the end of my talk.
You'll have a chance to ask questions of Andrew a little bit later on. I'd like to take over now and tell you about a subject that's rather different. I've spent too many years studying small bodies in the solar system, that's comets, asteroids and interplanetary dust, and learning about their physical properties and how those properties tell us about the evolution of the solar system. I'm not going to talk about that specifically tonight, although I'll cover some aspects of it during this talk. Recently, in the last decade or so, there's been an emphasis from research councils who provide the funding for us to try and demonstrate potential impact of the research that we do. So that's impact on society and value to the UK budget, total budget. So I thought I'd choose a subject which had a very literal aspect to the impact that it may have on the future of the UK. Okay. Asteroids typically lie between the orbits of Mars and Jupiter. So on the diagram on the right-hand side here, you can see the outer circle, Jupiter, and the second circle inside it, Mars. And all the green dots is a snapshot of the positions of the known asteroids yesterday. There are something like 700,000 of them orbiting between Mars and Jupiter, and they're in stable orbits, and they've been there more or less unchanged for the lifetime of the solar system, 4.5 billion years. And they are the fragments of planet that was never completed because Jupiter formed and stirred up the orbits and never allowed a new planet to form there. In fact, they are the result, as you'll see later on, of many smashed up bodies. A small number of those have orbits which put them into unstable positions, and they can go into the inner solar system, fly past the orbits of the planets. They may, in extreme cases, impact the planets, but more often they have a close approach and they're flung out again. And they have lifetimes of maybe only a few million years, but are continually being fed from the main belt. And those are the red ones. And you can see where the orbit of the Earth is in there. There are an awful lot of red objects that come into the region of the Earth, and many of those cross the Earth's orbit. Many thousand asteroids known that do it, many millions that we haven't measured yet. Okay, that could potentially hit us. So I've got a question which you might like to answer, and that is that if there are objects that are crossing the orbit of the Earth, potentially they could hit the Earth. Should we be worried about it? Okay, do you know of any objects that have hit the Earth recently? Do you care about it? Could we stop it anyway, even if we did know that something was going to come? And you know, is it worth spending the money to do it? Okay, so think about that and give me your answer, and I hope I'll persuade you that you might change your answer by the end of the talk. Okay, if we look at the closest body to us in the solar system, that's the Moon. The one thing you notice is it's absolutely covered in craters. And those craters, from probably the 1950s onwards, maybe 1960s, people recognized these craters were not volcanic. Mostly they are a result of impacts. The moon is peppered with impacts over its lifetime. The Earth is next to the moon, so there's no reason why the Earth shouldn't have been peppered with exactly the same number of impacts. In fact, somewhat more because it has a bigger gravity. Yet we don't see craters all over the Earth. And the reason for that is because the Earth has plate tectonics and the craters get erased. We only see in extreme examples big craters like the one at the top there, is 24 kilometers across, very eroded. It's about 140 million years old. And the one at the bottom, where I'm standing on the edge, that's Meteor Crater in Arizona. It's a very small one, and we only see that because it's very recent and it hasn't been wiped out by erosion yet. Okay? So there is evidence for craters on the Earth. And there's no reason to suspect these things haven't been hit as often, or if not more often, than the moon. But when you actually look at some totally different geological evidence, that is the fossil record, and you look at the number of species and families that are present on the Earth, you see that the growth of the number of species and families is punctuated by periods where there's a very rapid loss of up to 95% of all species. And these occurring on in time intervals of maybe 50 to 100 million years. And the last of those occurred 65 million years ago, and that was the impact, as it now turns out, that wiped out the dinosaurs. And the smoking gun was discovered not that long ago, a crater in Mexico that is completely invisible. The picture of the crater you see there is from gravity anomalies, so they're the way the density of the rock has changed. But you wouldn't know there was a crater there if you just looked at the ground because it's been completely eroded away. But the real smoking gun is across the entire Earth. There's a layer of clay at age 65 million years that contains elements such as iridium at much higher concentrations that you see anywhere else on the Earth, but typical of asteroids, as we evidence from meteorites we collect. So we know that something wiped out the dinosaurs 65 million years ago. Of course, could this happen again? There is one thing to say that, of course, you could argue that it was a rather good thing, because wiping out the dinosaurs left an ecological niche for humankind ultimately to evolve, which might not have happened had that impact not occurred. Okay, sobering thought. But there are impacts in historical times. Okay, here's the result of an impact in 1908, which fortunately happened in Siberia. The object never reached the ground. It blew up in the atmosphere, but it was enough to knock trees down over 2,000 square kilometres, and if that landed on a city, that would have been a huge number of casualties. Fortunately, there were none. And it was only found, the site was so remote that it took a long time for it to be visited. Much more recently, in all our memories, 2013, you must remember the fireball that came down over Russia. Russia seems to attract these things, doesn't it? That again blew up in the atmosphere, somewhat smaller, maybe only 17 metres across, but the air blast from that was enough to damage buildings, and about 1,000 people were injured, mostly by broken glass. But fortunately, nobody was killed. And some meteorites landed, and I actually have one in my pocket here, which, if you see me afterwards, people can have a look at it. So these things happen, and they're happening now. Okay? So the question is, are we going to get any more, and are they going to be bigger? And, of course, in order to do that, you have to go and hunt for them. So just in the same way that Andrew's telescopes are looking for stars across the sky, while you're imaging those fields, asteroids move across, and you detect them as moving objects and work out their orbit, and then you can calculate, A, if they're in an orbit that might cross the Earth, and B, if they might actually hit the Earth in the future. Okay, and so there are dedicated searches going on for this in parallel with doing astronomical observations, and LSST will be fantastic for this job as well, just as a byproduct. Okay, so that's great. We've got that. That's all kind of set up fine. But what do we find? Okay, so here we see a diagram with brightness along the bottom in some magical astronomical unit, which you don't need to worry about, but basically the bright objects have the low numbers at the right, and the faint objects have the high numbers at the left. And I've converted them into sizes for you at the top. So you can see at the right-hand side we have things that are tens of kilometres across, and at the left-hand side they're a few metres. And the red line is the number of objects we've found. Okay, and from that you can then determine based on how complete you think the survey is, how many you think are out there, and that's the blue line. Okay, so for the very small ones, we've only seen a tiny, tiny fraction, because that's a logarithmic scale up the left-hand side. Okay, so let's have a look at this. Okay, so the first big thing you want to know is, are we going to be wiped out, like the dinosaurs were? The answer is, if we draw a line down at about the size of the impact that caused the extinction of the dinosaurs, you find there are only about 10 objects that size around at the moment, and they, on average, will hit the Earth maybe every 50 million years, which is kind of about right with what you saw in that mass extinction plot. Yeah? If one does, it'll probably kill 5 billion or more. Most of the Earth's population will die from one reason or another. Okay? Fortunately, none of those 10 objects that we know now are going to come anywhere near the Earth, and they're no risk. Doesn't mean it's not going to happen in the future, because new ones may be coming from the asteroid belt. But we're safe. We're much more to worry about from our own activities on the Earth over the timescales that that's going to happen. So that's fine. Let's go down a bit in size to a kilometre. Okay? Here you're talking about something that could still kill 100 million people if it impacted the Earth, mostly through dust thrown up in the atmosphere, creating a nuclear winter. And this is the equivalent of basically all the Earth's nuclear weapons going off at the same time. Okay? And there are about 1,000 of these bodies. Fortunately, we found at least 95% of them, and none of them are going to hit us soon. So shouldn't worry about those either. We can go down to the very small end, and you've got millions of objects, almost all of which we've not found yet. Okay? A few meters in size, but they blow up in the atmosphere and don't kill anybody. And these happen, a meter-sized body hits every year. Okay? Something the size of Chelyabinsk might happen every 20, 30 years. Okay? So again, we don't worry too much about those. But once we get up to about 40 meters, on average, then you'll start getting casualties. But there's this horrible zone in the middle between about 100 meters and 400 meters, where you can see the red line and the blue line diverge. We only know of around just under a third of these objects at the moment. The 2/3 of them still to be discovered, and among those might be the one that's got our name on it. And these, look at the average casualties. That's average. Remember, most of the Earth is not terribly well populated, so if you land on a city, it could be millions. And the frequency of those, on average, is somewhere in the few thousand to many tens of thousands of years. And you might think, well, that's all right, we've got 1,000 years before the next one hits us. The trouble is, that's the average. The next one might be tomorrow. Okay, and so this is the size that people who are studying these objects are concerned about, because we don't know yet that there isn't one that's going to hit us. Okay. And what would happen if it does? Okay, well, let's imagine it targets Milton Keynes. Okay, that's the size of the crater from an object 300 meters. Okay, the crater is 5 kilometers across. If you're inside that crater, you're turned to atoms. Okay, no chance. Right, if you're a little bit further away, you're still a goner, because you'll be incinerated by the heat blast. A bit further away than that, you're still goner, because the heat is still strong enough to set fire to your clothes or burn your skin even further away. If you escape that, then the crater throws up lots of boulders. You might get hit on the head by a large boulder, or whatever happens in those circles there, you're going to be covered by a thick deposit of dust and so on coming down, which will affect the way, certainly will prevent any agriculture, for example. So you're basically in that larger circle saying that's no good to us for a while into the future, right? Even if it doesn't kill you. If you're inside that circle, you might die from earthquakes, buildings falling on you. If actually it landed in the ocean, it would be much worse, because you create a tsunami that could then flood much, much larger areas, and the casualty figures would go up from a few 100,000 to several million. Okay, but we're hitting Milton Keynes, so we're not worried about that. What we actually should be worried about is actually the worst effect, which is the air blast. So remember, this is what did the damage for Chelyabinsk. The people didn't really feel the heat or anything like that, but they felt the vibrations in the air, which broke windows. Most people were injured by flying glass. And the outer circle there is the region in which you could be injured by flying glass, and you can see it covers most of England. Okay? The inner circle is the region where you don't want to be standing inside a building because it may fall down from the air blast. And if you're somewhat inside that, your guts will be literally ripped apart by the shockwave that's passing through you. Okay? So, lots of nice, pleasant ways to die, I think we'd rather like to stop that happening if we knew it was going to happen. But do we know it's going to happen? Well, of course, if we do think that this is going to happen, we've got to stop something. This is where the work that I've done, which was scientific, comes in, because you want to know what the properties of the body are. So you have to know what it is that you're going to stop before you can figure out a way of stopping it. And just as with the stars that Andrew talked about, asteroids all the time look like a dot, as observed from the Earth. So the only way we can distinguish the dot that's in the little circle from the other dots, which are stars, is the fact that if I took another image an hour later, it would have moved. Okay, and from those positions, we can calculate the orbit, the changing position. But of course, we can't say anything about its size, because it may be that it's a very highly reflective small body that produces that amount of light, or it could be a very big dark body. And I know I'd rather be hit by the one on the left than the one on the right. But how can I tell which is which? Okay, and this is something that I've spent a long time doing. We use infrared radiation. So when you get the sunlight lands on a body, some of it is reflected. If it's small and highly reflective, then most of the light that lands on it will be reflected. And that's the green. So this is a spectrum with wavelength along the bottom and intensity up the side. And you see there's a lot of green. What is not reflected is absorbed, it heats the body up, and that's re-emitted as thermal radiation, heat, essentially, at wavelengths of around 10 microns. The sort of thing that we would see if we had a thermal camera on in this room, that's what we would be seeing. And that's the red. So you can see the difference between the case on the left and the case on the right. On the right, very little sunlight is reflected, and most of it goes into heat, and so the balance between the reflected and thermal light is different. And by comparing those two, measuring in the thermal infrared, and you produce a model for the temperature distribution on the asteroid, because you've added it all up, heat from different locations on the asteroid, and you can work out the size. Okay? And that's what I did in my PhD, with observations from the first infrared orbiting space telescope, to work out the size, in fact, to discover asteroids from their heat. We also want to know what they're made of. And we do that by looking at the spectrum of that reflected light. If you look at the spectrum and it's perfectly uniformly reflecting, if you divide its spectrum by a star like the Sun, you'll get a straight line. If it's not a straight line, that means it's reflecting light in a different way because it's made of different materials, just in the same way as this table is wood-coloured, those chairs are black, that wall is blue, they're reflecting light in different ways, which reflects the different materials. And on the left, you've got spectra of different asteroids and an alphabet soup of types there, which are all come from relating those spectra to the spectra of meteorites we see in the lab. And you can see the pictures here. Bottom right is an iron meteorite. The top one is a stony meteorite. The second one down on the right is a mixture of the two. So the iron meteorite will come from the core of an object. If you imagine an asteroid that's a bit like a mini Earth, its iron core has been exposed by a collision, and that's a fragment of it. Okay? And the third picture is something called a carbonaceous chondrite. These are very primitive meteorites that have never really been heated very much, retained their composition from the very early days of the solar system, 4.5 billion years ago. They're much less dense and much structurally weaker. And if I wanted to pick one of those to be hit by, I'd like the third one, because that's the one that does the least damage. Okay, so we want to know what the asteroid is made of. That helps us understand it too. And thirdly, we want to know what its structure is. And paradoxically, we can actually find out what the structure of a body is by looking at the light curve. In this case, the changing brightness of the light, as you can see in the light curve at the bottom, is caused by the irregular shape of the asteroid as it spins. So you see two peaks, two maxima and two minima, which correspond to the largest area and the smallest area as an elongated object spins. So it's very easy to work out what the spin period of that object is. And you can actually work out its shape by observing it from different geometries at different years of observations. But that's not really terribly interesting if you're going to be hit by this thing. You want to know what its structure is. And you can learn that from the light curves. If you plot all the periods of all the asteroids that we've measured against size. So on the bottom is the size of the body from the largest ones at 1,000 kilometers down to things that are a few meters in size at the left. And the spin periods are shown up the left-hand side. And what you can see, the first obvious thing you see is there's a massive missing place where there's no objects. And that corresponds to spin periods shorter than 2.2 hours and sizes bigger than about 200 meters. And what this tells us is that these things are structurally weak. They're rubble piles. Because if you have a body which is spinning fast, if you spin it faster and faster and faster, at some point the gravity of the body is overcome by the centripetal force, and you basically, things fly off. So you can't hold the body together if it doesn't have its own internal strength. It will fly apart. And that occurs at 2.2 hours. And the fact that there are no objects in the top right tells you that all those bodies are structurally very weak. They're made up of rubble piles. On the left, we do see things that spin much faster, and they must be individual rocks that are the fragments of these big collisions that have occurred in the past where you've reaggregated to make a rubble pile asteroid, and those are little bits that are left over that are individual solid rocks, and they're all smaller than 200 meters. The region that we're interested in is 100 to 400 meters, which straddles that. And of course, if we're hit by one of the ones on the left, it'll do an awful lot more damage than one of the ones on the right. But also, the mechanism that we use to stop it might be affected if it's a solid rock or if it's just a collection of loosely bound boulders. Okay, so this is important too. Right. How do I know that all those things are true? Well, we've been to a few of them. And it turns out all those things are true. The sizes are right. The structures are right. We can measure the densities of objects with a spacecraft orbiting around, and we find out their densities are much lower than the density of the rock they're made of, because they're full of holes, because they're loosely bound rubble piles. And they have funny shapes and weird gravity fields, and they're not very nice things to have to operate with in spacecraft. I should say the left and the right objects at the bottom there are being visited by spacecraft right now to bring samples back to the Earth. But our interest is in kind of using these few spacecraft measurements to verify what we know about the objects. Okay, so given all that, how do we stop one if one has our name on it? Not like this. Great fun, but I could give you a 2-hour lecture on the bad physics in these films. But summed it up, basically they were too late. Okay, there's no way they could do anything. They were always, it's always a last-minute cliffhanger on a film, and they stop the thing at the last day and the last hour. No. If you're going to stop one of these asteroids, you've got to do it years or decades ahead of time. Okay, and the way you do it is like this, or at least there are different ways of doing it. The three that are preferred because they are possible with today's technology are, first one called a gravity tractor. You take a spacecraft, you fly it very close to the asteroid, and you thrust the motor very, very gently. And the asteroid's gravity attracts the spacecraft, and equally, the spacecraft's tiny gravity attracts the asteroid. So if you just thrust a thrust lower than the escape velocity of the asteroid, the gravity of your spacecraft would pull the asteroid away. Now, the speed that you have to do that is such that it would take decades to move it far enough so that it didn't hit the Earth if it was going to. So you've got to be there early, and it only works for small ones. For really big ones, the spacecraft has to be too big and we can't do it. So then the second technique is a little bit more violent, and that is to whack it with the spacecraft at very high speed. And I'll come back to this in a few minutes. So this is called a kinetic impactor, and the impulse that you give the asteroid changes its orbital speed a little bit, and aggregated over time, that means it gets further and further distance away from the track it would have had, and eventually it would miss the Earth if you do it early enough. If neither of those methods you can do in time, then you do a bit of Bruce Willis and you set off your nuclear weapons. But you don't dig a hole and stick the bomb inside and blow it to pieces, because you then just get hit by lots of asteroids instead of one. What you actually do is blow it up off the surface. The heat of the explosion vaporizes material on the asteroid, and that produces a jet effect which pushes the asteroid away, in theory. We will never ever be able to test this because of non-nuclear proliferation treaties, and the risk of anybody trying to do a test launching a nuclear weapon into space, you can imagine. Okay, so, but the other two we could. And what do you do? Which one do you choose? Well, it depends on how long you've got and how big the object is. And in fact, if the object is smaller than about 70 meters or so, you just let it hit you. All right? You get everybody out the way from the place where it was going to hit, but that's cheaper and safer than trying to deflect it and failing. And so you rely on civil defence. But once the things start getting bigger, you saw the kind of damage they would do if they hit, it's worth trying to stop it. But you need decades. And you've got to be ready for launch for these things and arrive there and then have decades on top of that. And remember, the things that we've discovered that did hit us, we had, well, in one case we had 14 hours notice, and the other one we didn't see it at all. It just hit us. Okay, so this is why those telescope searches need to find every object and map their orbits out in the future, because we need to know it's going to hit decades ahead of time and then send something up to stop it. And the biggest problem is actually political will, because 50 years before the impact, you're not actually sure it's going to hit at all. You only know within a year or two, and then it's too late. So you have to launch the mission to stop it before you even knew it was going to hit you. You just know it might. Okay, and that's a tough decision to persuade politicians to spend a few billion euros, dollars, pounds, when you might not even have needed to in the first place. But the longer you leave it, the harder it is. Okay. So it's fortunate that we actually have a mission, finally, after spending many years studying these things, a mission that allows us to test one of these mechanisms. And this mission is to test the kinetic impactor process. The gravity tractor is great because you don't interact with the asteroid at all. So you don't really need to know what it's made of or what its structure is because you're just using gravity. So you could do that anytime, but it needs to be small. This one is more versatile, but it needs to test it because you need to know how the asteroid responds to the impact. And you don't want to test it on an asteroid and then deflect the asteroid into the Earth. So this test is great because it's using a binary asteroid. So it's an asteroid with a moon. So instead of changing the orbit of the asteroid about the sun, what it's doing is changing the orbit of the moon about its primary asteroid, which is kind of safe. And so there's two spacecraft. One was called DART, Double Asteroid Redirection Test, which is NASA. So NASA shoot the asteroid and ESA watch it. That was the idea. And you hit the moon and change the period of the moon's orbit around the asteroid. And the great thing about that is that this asteroid is observable in 2022 when this mission is planned to hit from the Earth with small telescopes, and you can observe the light curve and the eclipses just in the same way as Andrew showed you eclipses of stars. You see a little dip in the period and you can measure the period. It's going to change the 12-hour orbit by about 7 minutes if it works properly. Okay, so there's the test. Unfortunately, Europe decided to pull the plug on its bit, the observer bit, and you might think that doesn't matter because we've still got the test, the impact test. And I'll come back to why that is. The reason they cut this was because the Mars program was overspent and that was a higher priority. I don't think that was a wise decision, but there we go. So here we now have the DART mission from NASA. It's just starting construction phase and it's all go ahead for launch. It now has a launch vehicle assigned to it. Here's a radar image of the asteroid with its moon, and the spacecraft will hit the object and you will be able to test whether this technique has worked. So you think, why do I need an observer spacecraft? Why does ESA need to spend its money? And the reason for that is because of, and here I've got my one equation, is to understand, to be able to predict, based on this impact, what will happen with a different asteroid. So we've got something called conservation of momentum. Momentum is mass times speed, and it's conserved. So your spacecraft has a mass of MSC and a speed of V impact, and it hits the asteroid. The asteroid has its mass, big M, and it imparts a change in speed, big V. And so we know 3 out of the 4, if we know 3 out of the 4 things in that equation, we can work out what big V is, and then we know how it's responded. Now, the observer spacecraft is the one that was going to measure the mass of the asteroid, big M. The impactor can't do it because it's destroyed itself on impact. So that was the main purpose of the ESA mission. But it's a little bit more complicated than that, because when you hit the asteroid, you throw ejecta out the back. And the ejecta has momentum as well. And that has a mass and a speed, and that, because it's coming out back in the direction from which you impacted, also has a jet effect and gives you extra speed on the asteroid. So it's actually a gain, if you like, but you want to know how big that effect is. And it's measured by essentially a multiplying factor beta. Now, you can't figure out what beta is unless you know what all the other four things are in that equation. So you need to measure the mass, you need to measure the speed change, and you know the other two numbers. Okay, so you need the observer spacecraft there to do that. And so the idea is that you can do that to study the momentum transfer. One of the things that I've been involved with is using the light gas gun here at the Open University, a project called NeoShield, big international project, looking at all aspects of planning for this kind of mission. We were studying how that value of beta depends on different materials and different structures under lab conditions. And that doesn't mean anything for the asteroid because it's completely the wrong scale. We're doing impacts on this scale and the asteroid's kilometers across. But you can verify numerical mathematical models on the scale of the lab where you can test and set up the model. Then you can extend the model to regimes that you can't test in the lab, and therefore convert your test into a prediction for what might happen on the one that is really going to hit us, is the idea. And to do that, we have what's called the HERA mission. This is an observer spacecraft which is going to launch after the DART impact now because there isn't time, but it will observe the impact crater and study the structure of the crater, and it will measure the mass of the body, which allows you to make those predictions and extend it. So this is the verification, if you like. DART is the test to see if the method works at all, technically whether you can do it, and this is the verification to show that if we can succeed, then we can then apply it to every other object. And the cost of this, something like 250 million euros. The UK is not in. Everybody wants the UK to be in because that gives you confidence that other countries will join. Germany are paying probably for the majority of this. And they want something in the region of 10 to 50 million euros from the UK. Now, remember that question I asked you? I did a little look around to see what you get for 10 to 50 million euros. And I don't know what made me think of it, but I thought of, I was cleaning my teeth, and I thought, how much do we spend on toothpaste? Okay, we spend 500 million pounds a year on toothpaste in the UK. All right, but of course we've got the toothpaste, so I can't not have the toothpaste and spend it on a fraction of that on the. But if you work out that 10 to 50 million over 10 years, that is about 1% of the cost of the toothpaste. That's what you throw away in the end of the tube that you haven't used, all right? That's the kind of level of money. It sounds like a lot of money, 10 to 50 million pounds, but spread it over the population and over a length of time, it isn't very much, okay? Especially if you want to save humanity. So I'll ask the same question again. And any of you would like to vote now, having heard what I've said. And these are my answers to those questions. Thank you very much.
Hello, everyone. I'd just like to start by thanking both Simon and Andrew again, even if Simon's talk was a little worrying, shall we say. But thank you once again, both of you. We'll move on to questions in just a couple of minutes, but let's just thank them both again. I'll just start by introducing myself and then say how this game is going to work. So my name's Sally Jordan. I'm head of the School of Physical Sciences here at the Open University. I think you two both alluded to the fact that that's the school that you're both in. I am absolutely thrilled. I think I'm going to use that proud word again. Those of you that have been in this lecture theatre earlier on today as well know that other people have been describing themselves as proud. I'm incredibly proud that the two of you have here been giving the talks on Charter Day. It's great, so thank you very much. So the way in which we're going to run this is basically ask for questions. Katrina, I think you're going to pick up anything that comes in remotely. And Kath and Rachel have the microphones and will ask questions. We'll run like that for 10, 15 minutes. So has anybody got a question to ask of either of the speakers? If you raise your hand, there's one down here, and then Carol at back. There's two down here.
I would like to ask the first lecturer, Andrew Norton. You say that all stars vary in their brightness. Our sun is a star. Has it been studied with regard to global warming / climate change?
Yeah, I mean, is my microphone working? Yes. Certainly the sun varies on short time scales, on minutes at a very small level. It varies on longer time scales of decades, centuries, millions of years. Certainly it does vary on those timescales and has affected the Earth's climate as a result of that in the past. But, as I'm sure you know, what we're talking about in terms of human-initiated climate change is something that's separate from that. So it's on top of anything that changes in the sun may cause in our climate. The sun certainly does and has caused changes in the climate and will continue to do so, but that's in addition to things that we're also doing.
Thank you.
Thank you. Was there another one? Were you wanting this just next to you, just take time?
Thank you. The impact that you showed of the asteroids hitting the Earth was proportional to their size. Is there an element of their velocity which changes the impact effect?
Yes, I took some average conditions. So if you have, it depends on the speed that it comes in at and the entry angle to the atmosphere. So typically I took 45 degrees, which is on average what you would see. If it came at a shallow angle, the damage would be less. And it obviously depends on the density and structure of the impactors. But actually, the velocity is not so much a factor as you might think, because 11 kilometers per second of that speed is what you would get if the asteroid was traveling at 0 outside the Earth. That's just the Earth's gravity pulling it in. So the typical impact speed is 17 kilometers a second, which is what I used in those calculations. But you might get a variation of maybe 50% if you changed all those parameters. But, you know, it's 200,000 people or 400,000 people. You know? I don't think I like either of those numbers.
No, it's not nice. Okay, Carol.
Yeah, so I've got a question for Simon. So I think it's really sad that the ESA mission that was going to watch the impact got pulled. And it seems like at the moment there's a real push to doing space missions faster through a variety of different mechanisms. And I wondered if there was any chance of doing a crowd-funded mission, or are we just too late to launch it now?
It really is too late now. It was pushing it anyway. That was in 2016 when that decision was made. Europe makes its, or at least for the space budgets, they make decisions every 3 years. So the decision for this mission, which is not approved yet, will be finalised in the autumn. But we've already been spending money from the first one up until 2016, and then we had a delay of about a year and then started spending money again. But nobody's cut metal yet, and that's the problem, that won't really happen until the autumn, although we now know what we're going to build. So yes, you can build quick, cheap missions, but usually they're for Earth orbit. Doing anything interplanetary, it's 100 million before you start. So, you know, you can't really do it very cheap, unfortunately. There is one rescue to this, in that the DART mission has added something which I thought, it's called Lycia now, I can't remember what the acronym is. It was much better before. It was unofficially called SelfieSat. And it was a little tiny spacecraft that was ejected from the main spacecraft. And so when the impact occurred, it would fly past a few seconds later and take a picture of the impact. But it wouldn't get a picture of the crater because all the ejector would be in the way. But at least that will tell you at least that the impact had occurred in the right place. And there are images taken back from the main impactor spacecraft right up to the last second before it hits. But none of those things will tell you the mass, which you have to have the
orbiting spacecraft to do.
I've got another question which is a little bit mischievous. So if you knew that you had a near-Earth asteroid and you did one of your tractor missions, would you be able to do it with sufficient accuracy to divert it so it hits an enemy country?
Yes. And strangely enough, every couple of years there's a conference called the Planetary Defense Conference where we have scenarios. And we do scenario testing, so we put in over 20 years of sort of history into a couple of days during the meeting. And the last one I went to was a scenario in which an impactor was identified it was going to hit India. In order to make it miss the Earth, it was big enough that you couldn't do it with one impactor. You had to use 3. And all 3 had to work. If 2 of them worked, it was going to land on China. Right? And then we had people playing politicians. You have lawyers and so on. I mean, real lawyers present at the conference who play act the politicians from the countries. And basically China prevented any mission from flying for fear that if it didn't work fully, they would get the hit. And they paid India to take the hit. So politics comes into it. Yeah.
Oh, thank you. Katrina, are there any questions coming in?
Yeah.
Okay. Do you want to?
This is from John. John says, I understand there are around 7,000 plus NEA. Do we know which one is most likely to impact Earth and when? And any news of asteroids, I'm going to murder these, Bennu and yes.
There's a scale which gives you a sort of risk factor, if you like, from asteroids. And none of the known asteroids at the moment register on that scale. There have been some in the past, and one of the problems with this is that as you improve the observations, the precision of the orbit gets better and better. And something that had a probability of hitting, as the uncertainty gets smaller and smaller and smaller, the probability goes up and up and up, and then eventually what's always happened in the past is that the uncertainty has got so small that it's not on the Earth anymore and it's missing, and the probability goes to 0. And everybody says, oh, you said it was going to hit, and now it's not. And there's a sort of trust thing, because people don't understand how that process works. But there are objects for which we know that there are very, very close passes that may hit us in the future. And they may hit us not because we think they might hit when they have the close pass, but if you come very, very close to the Earth, the orbit is deflected. And a tiny shift in the position at which you pass the Earth makes a big change at some point in the future. And at the moment, we can't predict how close that miss will be well enough to know that it doesn't hit again in the future. So there are a number of objects which could pass through some of these what they call keyholes, which are critical distances, which may make them hit in the future with a small probability. But they're 50, 60 years away for those. The next one is an object called Apophis, which passes the Earth in 2029. Originally, we thought it might hit then. Now we know it's not going to, but it might get a deflection that will make it hit 30 years or so after that. If that's the case, we want to be launching one of these things to it, because it's over 100 meters in size. So, and there are a number of other objects like that. So Bennu and Ryugu are both, I think Bennu is the higher risk of the two. It's a very, very small probability, but it's not 0 that it will hit the Earth. But the likelihood is that once we improve those orbits, it will go to 0. But one day we'll find one where it doesn't go to 0, where it goes to 1. And then we know it's going to hit.
Okay. Anything else, Katrina?
Yeah, there's a question on SuperWASP. The SuperWASP project on Zooniverse gives the opportunity to categorize variable stars. Is there a way of carrying out more detailed work / follow-up, please?
Well, yes. I mean, the great thing about these SuperWASP objects is that they're all relatively bright stars. So perfectly within the capability of any keen amateur astronomer's telescope. I know there are a few very keen amateur astronomers in the audience. So yes, any of these objects could be followed up. Many of them, most of them probably, most of these variable stars have not been well studied. So there's plenty to find out about any of them. We, just to advertise something else, Nick mentioned at the beginning a bit about the courses here. We have a space science MSc course, and one of our students this year that's doing an MSc space science project is actually following up one of these super-WASP variable stars using the OU's own robotic telescope, which happens to be out in the Canary Islands. And she is monitoring that star and studying it for her space science MSc project. So there is scope to do all this sort of thing.
Lovely. We had a question from Susanna over there.
Yeah, also for Andrew. If you have the new telescope, that becomes a big data problem. Has anyone made the calculation how long it takes to just look through the data and classify them so you can do the follow-ups?
That's a very good question. Yes, astronomy is entering this era of big data, like many areas of science. And even with a relatively small project like super-WASP, we have more data than individually a few people can look at. For something like the LSST that I mentioned, that's going to be many orders of magnitude more data again. I think I read one estimate, and Alistair in the audience may know this number better than me, something like a million transient objects per night has been talked about, so that, you know, a million new supernovae or things flaring and going bang per night. No one's ever going to be able to look at all those. We're going to need machine learning, artificial intelligence, just to be able to keep up with all these new data. And that's, you know, just one telescope in one area of astronomy. It will be not a problem. It will be a nice challenge to have all these data that we can investigate.
I'm going to take, there's just one last question I'm going to take at the back. There will be plenty of time to carry on talking to these two afterwards, but some people I know want to get away. So, final question just at the back there.
Hi. I had a question for Simon. How do we quantify the risk of an impact from outer solar system objects?
That's much more difficult, because if you mean things, comets essentially, then those that we know about at the moment, we're safe from. But if comets originated in the outer solar system, and most of them during the migration of the planets early in the solar system's history were flung out of the inner solar system, way out into a region called the Oort cloud, which is a significant fraction of the way out towards the nearest stars. So they're barely just bound to the solar system. And when they're out there, we can't see them. We only see what are called long-period comets, comets that are new, if you like, coming back into the solar system for the first time. They have a very small perturbation, maybe from a star that passes, brings them into the inner solar system. They cross the inner planets and go out again, never to be seen again for millions of years, if at all. And of course, there's a chance for those to hit. Right? So the answer to that is, until it's coming in and we observe it with a telescope, we will never know. And the bad news is the warning time is too short for any of those methods to work. The other issue is that because they're coming in on very eccentric orbits, they're coming in at really high relative speeds. So you have to go out and sort of catch up with them. So you don't just fly to the object, because it'll be past you in no time at all, and you won't even have a chance to set off your nuclear weapon. You're going to have to match it. So essentially, if one of those is going to hit us, we're done for, right? The good news is the probability of that happening is, compared with asteroids, very, very small. So if you just calculate the mathematical probability based on the orbits that we see, it's less than 1% of the chance of one of the asteroids, which is orbiting in the inner solar system, of hitting us, because they only come past once, and they can come past at any angle. So the probability is very, very small. The consequences don't bear thinking about, but compared with the asteroids, you just can't worry about it.
We will, as I say, those of you who are in the audience will have the chance to ask any more questions. Any more that came in, we will make sure that they get to the right person, so you'll get an answer. I've got a few sort of random announcements to make, but before I do that, I'd just like to thank the speakers again, and also take the opportunity to thank, I'm not going to try and list who they are because I'll forget someone, but to thank all of the people who've made this possible this evening, including the two people who've been running around with microphones who didn't expect to be doing it. So thank you all very much indeed. And as always, the AV team, who are just always here supporting us. Right, the three things I just want to say. The first one is that, as Nick said at the beginning, this is the first of our STEM lectures. There will be more, so look out for them. In addition to that, I'm very conscious of the fact that we have one set of audience lectures that one lot of people go to, and perhaps another set that another lot of people go to, and I'm sure there's lots more like that. For those who are not aware, we have Institute of Physics South Eastern and London branch lectures that we organise in association with them on the second Tuesday of every month in the evening here. So if you aren't aware of those, want to be aware of them, have a word with me and I'll make sure that you get that information. Just to say, there's refreshments downstairs. I think some people felt that they were, if you like, for the great and good. They're not. They're for everybody. Everybody is welcome downstairs, so please do come. It's been a great day. A great end to it. And Simon will have the meteorite samples if I don't run away with this one here. And finally, I really have the randomest thing to say right at the end. Babette's asked me to say that around the place, as you walk out, you will see various displays of balloons. If anyone happens to have a birthday coming up or happens to want a balloon or anything like that, help yourself. So that has got to be the strangest thing that I've ever said. So thanks very much indeed and see you downstairs. Thank you.